Hello everyone, we're going to look at the task number 1, set bit count, of week 79 of the weekly challenge. Hey, wait a minute, why is it Pearl weekly challenge still? That's incorrect. Okay, nevertheless, so count bit, set bits. So you're given the positive number n, write a script, count the total number of set bits, so of bits with 1 in it, of the binary representation of all numbers from 1 to n, and return the total count bit set modulo by this number. That's a separate thing, but the task is pretty clear. So you've got number 4, for example. You have 4 numbers, 1, 2, 3, 4, and count bits in binary representations of all of them. It should be 5, and after that in this case this number is let's call this number means nothing for us, because number 5 is much less than this number. So nevertheless, this is the task. So just count all the bits which are ones. Right, let's go to the solutions. And today, let me first show my solution, because I have 2 different solutions. And the first solution, the straightforward solution, is here. Basically, what you can do in Raku, just take the number, no matter how you count, how to take it from the command line, and after that just find all the ones in the decimal representation. So that's the dot base of 2. This is the thing that gives you the binary representation. So all the characters after this are either zeros or ones, and you just can use regex to find all those ones, and after that you can just count the number of such found cases and repeat this for all the numbers starting from 1. Well, actually you can start from 0 as well, just to simplify this thing a bit, and after that just add it up. That's it, so simple. Let me run this solution. Raku Raku ch 1a. So this is for the number 48. Of course, if you will have the bigger number you have, the slower the program becomes, right? Because you just need to convert all the numbers in this range. But there are a few approaches that you can make an extremely quick program. So for example, this one, the same program with the same number, you see, so I can do even 2, 3, 4, 5, 6, 7, 8, 9, and you get the result immediately. You cannot do that with the previous version of the program. So how it works? Well, that's a bit tricky, but basically you have to notice that if you will just spell all those binary representations of all the numbers from 1 to the to your given number, then you will see that the smallest bit flips every second time, the second bit flips every fourth time, right, and so on, and basically just here you want to count how many times those bits flip in all the numbers. So you see, so actually the only loop here in this program is not over the numbers themselves, it's over the powers of 2 up to that number. So first of all, the loop is much smaller, and second, I don't count bits. I just actually what is written here it's too many words. Definitely you can simplify it, but if, for example, the number is 5, it's 1 unit bigger than 4, the previous power of 2, and you have to basically all these dash frac things are just to understand how many bits you added after the previous power of 2. So that's a bit, I have to think a bit about how to calculate that, but nevertheless the result is correct. I proved it for different numbers, so that's the algorithm, and it works quickly. Okay, so let me finish with my solution, and after that, today I will not go from the beginning of the list. I will just try to group the solutions, and let me start with this one, Rakulius, definitely the new name for these challenges, at least in the recent weeks. But here is one of the classical solutions this week. So what we're using, so we're reading the number, prompt is a good thing. it returns a string, and we are going to count the bits. How do we do that? So we organize the loop, and inside the loop body, we increment the counter, and we count. So we add up using the reduction operator with a plus inside all the characters, basically, right? Yeah, they will be implicitly converted to a number. So we have this binary representation, and we split it into characters using the comb method. And after that, we have 0, 1, 0, 1, 0, 1, and we can just add them up. 0 we kind of ignore, and yeah, this is the number of bits in the current number, and then just increment this. And after that, you can print this. Yeah, of course, yeah. So you have to do this. I forgot about that, but yeah, excuse me for that. So yeah, so let's run this Raku. Too many Raku here, and one more. So we need the number. No, we will be asked to enter the number. Total number. Yeah. So my test case is number 500. Which is a really interesting result, 2222. Okay, so it seems to be correct. Of course, yeah, you cannot use this number. It will be just very, very slow, but that's not the point. Okay, so it was Rakulius. The second on my list is Simon Proctor. And here is another solution. So again, we are reading the unsigned integer from the command line. We're saying something, so we add up using the reduction operator for all the n's in this range array. So yeah, basically that's a good thing, because we don't care about their order. We have to process them all, but yeah, who cares in which order? So we can parallelize this task, and then we map all those numbers to something, to this. Basically, again, so we take the binary representation of the current number, we split it into characters, we flat that, and after that we add it up, and after that, yeah, we make the final decision. All right, Simon Proctor Raku 1, and like yeah, let's test everything on this number. So yeah, it's 2222. Good. Okay, next is Arne Sommer, and his solution is here. So again, so we are reading an integer, it should be positive, and we map all those numbers to this. So basically we just see, so again we converted to binary, but it's a bit different. It's a bit different because we use this formatting stuff, and maybe you want to see. So for example, we have my number 42, and what happens when you do it like this, base 2. So you see there are just bits, but basically n base 2 what is a string, so that's the string. What you do if you have it like this, fmt, what was there, %b. So that's the same string, and the thing is that there's no prefix 0b, so that's an important thing, because after that we're going to apply this to all of those. Again, the order is not important here, and then we split into characters, we flatten the list, and we take the sum, right? That's it. So that's basically the same type of solution. Raku Arne Raku 1, number 500, 2222. Okay, the next is Colin Crain. The next is Colin Crain, Raku number 1. Here is the solution. So we take the number with some default, and the total number, we add it up for all the numbers. Actually, we start with 0, but that will not change the result, obviously. We make this binary, split, and count. Raku, Colin Crain, Raku 1, 500. Oops! The result is incorrect. For 3 it should be 4, and wait, I believe something is a bit incorrect. But why? It looks totally correct to me. But I don't know. Yeah, of course. Wait. we don't have to do it like this. We have to, so let's just fix this solution. Let's just yeah, well, basically you have to do it like this, right? Because we have to include the last number, right? We have to include the number, and Raku T500, yeah, now it's included, so we cannot skip that. But yeah, but in any case, so you can do it like this, you can do it like this, but then you have to increment this number, which is kind of strange. Okay. The next is Laurent Rosenfeld. Laurent Rosenfeld gives us this. So again, we see this formatting with %b, then comb, then sum, and then reduction operator, and we map using this scene. What we do map is just basically the range from 1, the range we saw just a second ago. Raku, Laurent Raku 1, SH, will it? It's not Raku anymore, right? 500. Mission denied. Okay, let's just then do it like this. 500. Right, the result is correct. Okay, next is Mohammad Anwar. And the solution is here. So we take some input from command line and we count the bits and we print the result. So we start with this range. Well, we start with 0. Then we map the range, and we're using the pointer block, the anonymous function, with the signature $I with only one parameter, which is actually the number. And then we increment the count, the total counter, by adding up all the characters. Yeah, characters, we convert them to numbers from this binary representation. So yeah, seems to be correct. Raku Mohammad Raku 1 Raku 500. Now I want it differently. Right, the result is correct. Okay, going next. Who's next? Next is Markus Anderson. Markus Anderson is here. Right, so again, the range, the map, we map all those numbers, we convert to binary representation. Then it's a bit differently. So then we comb, and we see, so for the first time today, we see that the comb also accepts the, maybe we have to go to the docs Raku. Wait, where's my history? Comb. See, so this comb also can take the string. Where's the explanation? So the matcher and returns non-overlapping matches limited to limit. If matcher is a regex, each match object is converted to a string unless match object is set. Well, not very clear. So, but okay. So here, for example, we have 3. It's not regex, but here we have regex. So yeah, see, so we have this semicolon separated list of word sequences, of word characters actually, and we have all those word characters, right? So yeah, now we just comb with this, we pass this regular expression regex containing a single one, a literal string, and yeah, so we will have all those ones there, right? And then we just count the number of them. So we see, so it's a bit differently, and after that, yeah, add this mod, and that's it. Right, so let's run this. Raku Mark Anderson Raku, what? Raku 1, oh my god, Raku 500. The result is correct. Okay, going next. The next is Ulrich Rieke, Raku number 1. Here is the solution. So see, so there are already more characters in the solution. So we accept the number. What we do next, we then just create an array of string representations. Actually, this .str is not necessary because we saw that this is already a string. You can prove it by printing the what, the result of what method. method. Then ones, so yeah, the ones, we count ones in this number, right? And in each of these numbers, in each denoted by map, and we'll just add them up. And so how do we do that? So this is a bit differently already. So there's no explicit comb, but what we do, we just loop over the characters of this string, and we basically take for the test every character, and if this character is 1, we increment the number of. So yeah, so basically, once again, so we take the binary representation, then we scan over the characters, and if the character is 1, we count it. Right, so Raku, Ulrich Raku Ch 1, Raku 500. Yeah, so and you see, so yeah, I like this output because this is the number, and this is the number that is required formally. Okay, next, Jaldhar. Where is he? Hey. Okay, let's just find it. I saw him. Oh my god. Yeah. Right, so this is the solution I was willing to look at now. So we take the positive number, and the total number is, you see, so that's already some modifications which are really interesting. So again, we are looping over the range, and we apply something to all of those numbers. That's fine. But what do we apply? So basically, it's a small function that first prints the number to this binary representation, as we saw before with %b, the printf format. And after that, we globally match all those ones. This is what I did, right? Kind of in my solution. Yeah, and then you will have what? You will have something which you will want to use in addition. Basically, you have to convert it to number, and basically it's the number of the elements that you found here. And after that, you just add it up. And right, so Raku Jaldhar. Why I never yeah, Raku Ch 1 500. Yes, this is the correct result. Okay, so the next solution is here, Raku number 1. So yeah, here's this solution. So we start with this range as usual, then we count the bits. And how do we do that? So basically, that's the main procedure. You start with this and then you divide it by 2, and you divide as many times as you can before the number vanishes, and you increment the count. And how do you do that? Basically, you modulo it by 2. It means that you get the last bit of it, right? So, and the last bit is either 0 or 1, and you increment this counter if this is 1, and you append 0 if it's 0, and that's it. So yeah, you repeat this for all the bits in the number while you can, and after that you've got the number, and you repeat the procedure for all the numbers in the range, and then you just print, well, double curly braces. Okay, right, so then let's Raku Ch 1. We need the number, obviously, 500, and that's the thing. Okay, let's go next. The next I propose to look at the solution by Roger West. Here it is. So what we see here, well, yeah, there are a couple of tests. Count set bits, the function which, so yeah, the number of bits, the thing to divide. Right, so we scan all the numbers, right? $n as a number. We keep it in the variable. For some reason, I don't know why we need it, actually. Yeah, probably don't want to divide this thing. Right, so but nevertheless, so okay, so you do kind of the same as in the previous solution, but instead of dividing, you just shift bitwise, right, by 1 position to the right. And you, again, count the bits by just taking the least significant bit. So you execute the bitwise AND operation with only with a single bit, and you, regardless if you get 0 or 1, you append it to the result, and you repeat it for all the numbers, and finally you've got this modular thing. And that's it. Raku, Roger, Bell West, Raku, 1, 5. Oh, no, there are some defaults. And the defaults are the defaults from the description. I believe this is correct. Okay, now we go to Krnavek. Krnavek, Raku number 1 is the solution. So we start here, the main function. There are half a dozen of test calls, and you see, so there are two functions, count set bits and count set bits, set bit big. So for small numbers we have one function, for big numbers we have another function. Where is it? It is here. And also if you call the function for small numbers with big number like this, more than 99, then you will automatically be transferred to another function. But okay, so let's look at the first function first, count set bit. So we scan the range and we map it. I don't quite understand actually why we need to and then. Yeah, that's cool, but you don't need it, just parentheses dot map, right? But nevertheless, then you call this polymod. Polymod. So basically you divide and divide by 2 by 2 by 2 by 2, and you take the mod of that division, right? So basically it means that you divide by 2, you get the least significant bit, right? Then you divide what remains by 2, so you divide the original number by 2, and again take the next least significant bit, and so bit, and so on, and so you scan all the bits, and after that you can just add them up, right? So whether it's 0 now or 1, you will get the sum. Okay, so this is clear. An interesting approach. The big thing is polymod. Okay, so you do in the beginning the same, but you do not do it for a range. You do it only for the number itself, for the big number. And then, so here we've got only zeros and ones, right? So we ignore all the zeros, right? And we take the index of that, we reverse that, and we map that. Wow, that's something, so some algorithm, I believe, right? So then, right, so we map those indices of the positions of set bits. We map that to that, and after that, so this mod is this big number, so we make this summation, and right, and going to return this. But okay, so this is what we are going to do. This slash, what does that mean? Probably okay, so so you x mod, so you like do x to the power of y and then just do the mod. Yeah, okay, so there's some algorithm behind this, definitely. Let me skip understanding of that, but nevertheless we can just run this program, right? And you see, so count set bit, so this is quite a big number, right? Like what this number is, and we can run this Raku. So this is, wow, really? So yeah, it should be really fast, I believe. So Raku 1 bash Raku 1, voila, test. Wow, yeah, so yeah, no comments for the last thing, but nevertheless, so we managed to compute. I wonder if I will be able to run this Raku 1 for my program. Cannot convert infinity to an integer. Okay, so somewhere interesting. Okay. Well, yeah, it beat my solution and beated my solution in sense that it can work with this number. But yeah, nevertheless. Okay. So yeah, so it was the solution by Krnavek, and we have a few more solutions left. They are okay. Let's start with Markus Holzer, Raku number 1, and I believe there are more than one solution here, right? Not. Well, actually not that much, but there's bench, faster. So there are a few approaches. Actually, I really recommend you to go through this file and see the different approaches to the same problem. But in the end, Markus submitted the main solution, which is the fastest solution out of those in the previous file, and basically it implements the algorithm, I believe, similar to what I had, right? Yeah, you cannot explain what happens here directly, you have to think, but the second like factor to make this fast is just to use sigless variables. You bind and see, so it's not only sigless, but it's only you see, you do not assign, you bind the so you do not create the new container every time you make these operations, and especially this is in loop, so yeah, you keep reusing the space. Probably maybe we can even put this outside of the while loop, maybe it will help just a bit, but nevertheless, so Raku, Markus Holzer, Raku Chair 1, and guess what I'm going to do? Yes, that's cool. So it works. So yeah, well, of course, let's try this on something that we can check. Yeah, that's correct. Cool, very cool solution. You don't understand how it works, you have to really try to deparse that, but the solution is really cool. Okay, so what we have left, it's Athanasius, definitely. Let's where is it? Athanasius, it's here. Raku number 1, Athanasius. So the solution, right, so there's basically, yeah, so there's this sequence on this website. You've got this sequence of number of bits in the sequence of numbers, and there's some algorithm behind how you compute these numbers, so you can just implement, and this algorithm, definitely you should use something like that, or like I used, or Markus used, or Jan Krnavek. For big numbers, definitely for big numbers, you have to make something smarter than just counting bits. So yeah, here's the thing. So fast C++ function for computing this the next number. So that's the algorithm. Voila! Just try to understand. I believe it's more or less the same that I used there, right? But right, let's look just at the, so we take the unsigned integer, defined integer from the input, and for yeah, so for bit, so we increment this bit, and so basically we scan all those powers of 2 which are less than the input number or equals to it, and we make some computations by using some binary shifts and stuff. Right. Okay, let's run this solution. Raku Athanasius, Raku Chair 1, 500. Yes. Yeah. Now all the solutions I want to pass through this filter. That's amazing. Amazingly fast, right? So yeah, I don't like that my solution breaks. Wait, actually, cd ash Raku HCBP ls GCC Chair 1 Raku. It's not Raku. Yeah, I believe it's, yeah, it will not be able to do that. Ooh, none of my solutions work. Okay, with this big number. Okay, cool. So the next solution is, let's go to Julio de Castro. All right, here it is. Julio de Castro. So here's another solution which is not like fall into one of the standard categories. So we start here. We use this calculate call. There's no parentheses, but nevertheless, that's the perfect Raku thing of calling a function. So calculate, you take the number again. These are all sigless. Some accumulator, return accumulated modular module. What is module? This is this one. If number equals 0, I believe this is if number so probably we call it recursively, right? Yes. All bits besides the first need extra flips. Extra flips are equal to the number itself. Okay, so I believe extra flips next accumulated. We also somehow try to count the flips, ms flips. What is ms flips? Given a number, it calculates the flips of the most significant bit number. E.g., this of 131101 returns the number of flips for number 8. So yeah, for this bit. So that's the formula, yeah. And next number is, where is it used? Where is it next number used? I don't see this. Next number. Yeah, calculate next number, and it's current number minus this thing, 2 to the power of this number of flips. Okay, yeah, so yeah. All right. Okay, so yeah, let's look at this solution. All right, so Raku Julie or Raku 1 500, and the result is correct. Okay, so what's left in my list is the solution by this guy, Myoungjin Jeon, Raku number 1. So here's the solution. So where we start at the beginning. So the thing for module operation. So we truncate. Actually, that's the function, right? Or what? As spec requested, but no need in Raku. Big number. Yeah. Well, so it's a function, right? So this is how you can create a function. Really? Wow. That's the whatever code block, if I'm correct, right? So this is a star, which is filled with an argument when they call this trunk. Actually, let's just look. Yeah, see? So, that's a very interesting thing I want you to show. So, I don't know if you see this, but basically, these are these circles. It's not Perl in sense of jewelry, but it's this thing here. I already have it here in search box. Right, so this is the infix, which can give you which can combine two functions, like functions on the left, f, functions on the right, g, and basically it's the same as you call the second function on the result of the first function, right, or vice versa. So that the left function is called with the return value of the right function. So basically, yeah, it's a different notation. It's very, very mathematical notation, but it's a different notation of just calling the function one after another. So we see, so this you truncate and then you say, that's cool. You're gonna use kind of dot, just regular ASCII dot to call .say, for example, but you can, yeah, and you have to swap the functions, the other positions. But here you just, actually you can use parentheses, right? Because the left function is called with the result of the right side, right? Then this left function for this operator is called with the thing that is returned after this call, trunk, right? So first we count the bits, then we trunk this, then we say this, and trunk is doing this, so it's a whatever code block, and we have the first argument that this function receives. It puts it is put here in place of this star. So basically, yeah, we got this modular. Okay, then naive. I wonder. You can use this I with with two dots right above to make it even cuter. Right, this thing. Okay, so this is naive implementation of the function. So yeah, we saw this a few times. So you take the binary representation, you count. Well, you find the positions of ones in that string, and you count the elements, so yeah, basically of the number of indices, and you do it for, yeah, so you see, so here we have this +1. There was one solution with an error off by 1, and then we add them up. Okay, then this is the naive thing, and are we going to use it anywhere? Right, so it's just for the test. But the main thing is, I believe, count set bits. So there's a helper function sum up to power 2. So we've got this power bit sum between 0. Okay, yeah. So that's like, for example, if I'm correct, if the number is like 5, so we count this for the number 4, and then we add some addition, if I'm correct. Yeah, so yeah, I see. So this is the power at m, and so basically this is 2 to the power of m, and we subtract that from our n, from this one, and after that we do something. Basically we just add it to the result, right? And count set bits for this remaining number. Okay, right. This looks cool. Actually, I like this. So basically, I believe this is Maybe we can even try to do this in the command line in the REPL environment. So what we need my m, well, 0, my n is, for example, 500, and I want to do this. So here I shift to the right side to the smallest bits, right, to the least significant bits, and basically I divide by 2. This plus indicates the bitwise operation, and this is the shift, obviously, and equal signs is basically well, it will assign the result back to n. So we divide it by 2 by 2 by 2 by 2, and while we can do that, we just increment the m. My n is 500, and do this the same. Okay, m, there's no result for this range, but yeah, m is 8, so 2 to the power of 8 is, yeah, basically 256. The next is 512, which is already bigger than this. Okay, so yeah, this is that's cool. That's really cool. That's really cool. Yeah, I will take a note. Okay, all right, then, so yeah, there are 2 cool stuff here. So this is, well, it's kind of cool, but not necessarily, not a necessity, but you can use this. Okay, so let's call this, where am I? Where am I? How did I land there? Raku Jeon, Raku Ch1. There's a short solution, okay. Raku, so I believe I need some number. That's correct, but let's look at the second thing, short, remove debug code. Ah, wow, that's cool. Ah, yeah, that's the thing that was called naive there, but again, you see, so that's cool. I don't understand why we need that, but I like that we can do that if you want. But yeah, if you read mathematical papers, you can see this kind of stuff. Okay, so yeah, and there's 1 or 2 left. Yeah, well, actually, there's nothing left, so we covered all the Raku solutions that were submitted last week for this task of the week 70 what? 79. Okay, yeah, see you next time. Goodbye.